Yeah, the recording has started. So today we'll be going through my review of the research paper titled Exploring the Frontiers of Vision Language Models, a survey of current methodologies and future directions. So in this research paper, they have gone through a list of computer vision models and how they are different from each other, which is better, and how the field is going to change in future. So we'll be reviewing this paper. I have published a Medium article for the same present over here. Let's go to the paper now. Yeah. Now, why do we need computer vision language models? Well, LLMs have catapulted the AI revolution. The only limitation is they can only handle text. However, we want them to be able to do more than just that. We want the new machine learning models to leverage for the LLM capabilities for other tasks, such as you have vision, you have sound, and so on. This is where computer vision, vision language model comes in, where they mix together uh, both of the two things. Now, what is a vision language model? Well, vision language model combines visual and textual information, showcasing a remarkable proficiency in comprehending and generating content. So that is, it combines computer vision and text and generates responses based on that. Now, these models are really good at captioning an image, querying an image based on your prompt. So you can ask where a particular thing is present in the image, it can identify that. And then image generation based on prompts. If you have used GPT before, you are familiar with Tally, or Adobe has their Firefly. That's basically image generation based on prompt. Those things are vision language models. Now, this paper categorizes models into three categories. First is vision language understanding models. So these are models that are built from ground up to understand images and language. Then you have text generation with multimodal input models. So here the image will be taken as an input, but the output will always be a text. And the next is multimodal output with multimodal input. In this case, the input and the output can be of any form. Now let's look at, so these are the three categories, and each category has a bunch of models in them. Now let's look at the first category, the vision language understanding models. And before we do that, this is the standard architecture of how these two work together. You have an LLM decoder, and you have a text and image. So you get the text is encoded in text encoder, the image is encoding using image encoder, and then it goes to image text fusion layer, and then back to LLM decoder. Here, frozen means it is a when you fine tune a model, will this thing will change or no? If you are not able to change that, then it is called frozen. If you're able to change that, then it is trainable. So for most cases, the image decoder will be frozen. However, image encoder will be frozen. However, there are cases where you can have it trainable as well. Now, let's look at vision language understanding models. First is CLIP. It is made by OpenAI. It is really good at zero-shot classification. However, when you give it a really fine-grained classification problem, it struggles. Then there is alpha clip. Alpha clip basically it's clip but with an added alpha layer. You can think of alpha layer as a transparency or opacity. So it helps increase its focus. And then meta clip. Basically, the beauty of clip model is from its data and not the model itself. So in MetaClip, it has a better training data. It is basically the same training data as Clip, but the quality has increased, and at the same time, like along with the raw data, it has also been trained on the metadata of the photos, and because of which it outperforms Clip in all the benchmarks. Then Clip is basically a version of Clip which focuses more on object level alignment and object detection. It outperforms Clip in image captioning and object detection. Then you have VLMO. It utilizes a fusion encoder transformer and uses the mixture of modality experts approach for enhanced flexibility. excelling in vision tasks through stage-wise pre-training on large-scale multimodal data. Then the other model is ImageBind. Aligns multi. What ImageBind does it? It aligns the basically image have their own embedding, sounds have their own embedding, text have their own embedding. So it aligns all the embedding to a common form and then uses them for learning and prediction and everything. All of it is really good at zero shot classification. Then you have video clip. The video clip is an unified zero shot video and text understanding model using a contrastive learning framework with loosely overlapping video text pairs and a retrieval based negative selection. Achieving state-of-the-art result on tasks like U2Cook. This is basically a data set, one of the benchmark data sets on which all the models were tested. And then you have Video MAME, which is like, it is basically, it uses mask on encoded video for doing everything. Then you have text generation with multimodal inputs. So these are models which can have multiple different types of different modes of input, but will output will only be text. First, you have GPT-4. Everyone knows what that it is. Then you have Lava. So Lava is basically Clip's vision encoder with GPT-4. Flamingo, this I think is made by Salesforce. Flamingo it works on cross attention and frozen self attention layers. It is really good at few shot learning. Then you have Palmy. So this is for robotics purpose. So it is developed by Google. It takes in integrates the language understanding with sensor input for robots and visual tasks, excelling in embodied reasoning and vision learning tasks while facing challenges with low-level languages, conditioned policies in robotics, and so on. Then you have Blip. Blip uses the VLP framework, so that is a vision language pre-training framework featuring a multimodal mixture of encoder and decoder architectures. So for each data type, you have separate encoders and decoders, and tackles noisy training data, enhances data quality, and achieves superior performance in image text tasks. Blip 2 is basically a cost-effective uh, it introduces a cost-effective pre-training strategy with static image encoder and large language model connected with querying transformer, enhancing in the interoperability between visual and language modalities for efficient parameter use. Then you have a bunch of more models. Out of this, the IDFIC is something of interest where it's an open access model. There's two versions, one with 80 billion parameters, another with 9 billion parameters. It shows really good results in image text benchmarks, such as questioning where a particular thing is in a image. And it is really good at few shot classification. Then there are a few other models you can read about them. The one which I want to talk about is QuinnLV. Is basically the QuinnLV series comprises model tailored for diverse vision centric tasks. So these are the models which are trained for multiple number of tasks. They are excellent in tasks like captioning an image, answering question based on image, dialogue, and especially they work really well with high resolution and fine-trained data. And at the same time, this model is also trained on multilingual data. Then you have MiniGPT and MiniGPT v2. Well, these models integrate a visual encoder with LLM using simple projection layer focusing on tasks like meme, MEM interpretation and visual question answering. The MiniGPT v2 specially uses the task-specific identifier and three-stage training strategy to enhance visual grounding and multitask learning efficiency. Then you have Lava Plus and Baklava. This was one of the original Lava was the language understanding model, and the Llama Plus is text generated through multimodal input. Then you have Video Llama. This Video Llama is designed. It's basically from Facebook. Video Llama is designed to understand both the visual and auditory content in videos. integrating pre-trained visual and audio encoders with frozen large language models. So if you recollect the architecture, the LLM decoder is frozen. That means you won't change the weight, and it uses the specialized Q formers for temporal and audio information, effectively aligning audio visual data with the textual content and enhancing comprehension in multimedia context. Then there are a few other models. There are actually a lot of models in this range. There are over 30 models just for this category. So you can refer to the Medium article or my summary to get a more detail on what each and every model does. Then you have multimodal output with multimodal input. So here the input can be an image or a text, and the output can also be image or text. The first is Cody. Cody uses LDM, that is a latent diffusion model for text, image, video, and audio. It features a variation of BERT and GPT encoder for text and LDM with VAE for images, and same the VAE encoder for audio tasks. Then you have Cody 2. It's basically an advancement over Cody. It uses it uses a multimodal encoder, unlike previously where you had a different encoder for text and different encoder for sound and so on. So here you have a single multimodal encoder with a multimodal latent language model for a detailed interviewed generation. Then you have Gemini. The Gemini features a transformative architecture with deep fusion capabilities to integrate text, image, audio, and video. It outperforms GPT-4 in most benchmarks, utilizing Google's GPU or TPU for training. The model emphasizes quality safety and has undergone extensive safety evaluation, including reinforcement learning from human feedback for bias and toxicity check. The only issue with Gemini is that it uses much more compute power for same amount of computation as compared to OpenAI. Then you have few other models in such case. Now, future direction. Where are these models going? Well, modularity in training. Now, traditional training methods for vision language models are often opaque and resemble black box. That means you don't know what exactly is happening. The move towards modularity aims to increase the understanding, control, and faithfulness by structuring models into understandable and controllable components. You want to get the model into separate components so that you know what is exactly happening. This approach helps to elucidate how different parts of the model contribute to the overall outcome, making the system more transparent and easier to adjust over time. Incorporating fine, this the same point it extends on the top. Then you have a fine-grained evaluation of models where efforts like DALI, that this is from DALI-VAL and VP-VAL are focused on evaluating the models more meticulously on aspects such as biases and fairness. We need to find a better way of evaluating the models basically. And they are crucial to, because the better you can evaluate the model, the more faith you can have on it and regarding its capabilities. Then you have causality and counterfactual capabilities. Well, inspired by similar advancement in LLMs, there's a significant interest in equipping the vision language models with the ability to understand causality and counterfactuals. This involves enabling models to reason about what if scenarios and understand the implication of changes in input, which is vital for application requiring deep reasoning and hypothetical analysis. Continuous learning and unlearning. Basically, we need to find a way where we train the model every other day and get rid of the parts which are not needed. Then we need to make the learning work is going on to make the learning process much more efficient. Right now, it's a very the models are very big, and you have seen the 80 billion parameters so far, 90 billion parameters. The models are very big, because of which they take a lot of time and money for training. We need to come up with smaller models which can be cheaper to run. Then you have multilingual grounding. Well, so far from all the models we studied, there are only a few which worked with multiple languages. So more work is going on having a model which works for all languages. And then you have domain-specific VLMs. So basically, vision language models which are really good at identifying certain type of skin cancer, or vision language model capable of identifying silicon defects in silicon chips, and so on. Well, that's the end of my presentation. Thank you.